Unsiloed podcast is produced by University FM, elevating the stories of your institution.
Welcome to Unsiloed. This is Greg LeBlanc, and I'm here today with Michael Strevens, who is a professor of philosophy at NYU, also the author of a number of books. I think your first one was called Depth, an account of scientific explanation, or did that come after Thinking Off Your Feet? I can't remember.
Actually, my very first book is about complex systems. It's called Bigger Than Chaos.
Well, okay. I need to go and get that one too. And so this other book, Thinking Off Your Feet, is sort of a defensive armchair philosophy. And the latest book is this one called The Knowledge Machine: How Irrationality Created Modern Science. Welcome, Michael.
Thanks.
Well, I have to say, this book, Knowledge Machine, I mean, this was really, to me, a profound work. It really altered my whole view of how science works. And I think you're trying to address a couple of questions. One is, why is it that the science, I was going to say the scientific method, right? But why is it that the rules of science have been so powerful, right? Why are they so successful as opposed to these alternative views of understanding the world? And then secondly, given that it's so powerful and so effective at helping us to control and manage the world to our benefit, why is it that it took so long for us to kind of figure this out? Right? We've been kind of thinking humans for a couple 100,000 years, and it's only in the last couple hundred years, right, during that period in the 1600s, that this whole thing really kind of flourished. So you talk about Popper and you talk about Kuhn, and these were the two folks that I had to read when I was in college. I don't know if people are still reading them as much as we did back in the 80s. And so they kind of jump-started this whole, I guess, philosophy of science literature. And I think you're trying to show how both of them were onto something, but they missed some essential insights. So I was going to say, tell me in a nutshell, but I don't want you to do that. We got a whole hour to play with this. But, you also do emphasize and you acknowledge the role of motivation in the world of science. And so I guess I want to ask you, what was your motivation for tackling this? Were you kind of like Thomas Kuhn, who sat down and kind of absorbed and channeled Aristotle and had this aha moment? I mean, did you have an aha moment that made you realize that science is fundamentally irrational in some ways?
Well, in a way, funnily enough, at least one of my biggest aha moments, and I think I mentioned it briefly in the book, was reading Thomas Kuhn, who I'd read like you, as an undergraduate, and kind of digested it in a way that made sense for passing that class. But I think I hadn't fully absorbed what I thought was really most rational about Kuhn's thinking, which is not actually the thing that most people take to be the biggest insight in Kuhn. But it's before he even starts getting on to talking about scientific revolutions and so on, which is what he's famous for and what the book is titled for. He's talking about non-revolutionary science. He calls it normal science, and the way it works. And the picture he presents of normal science is really quite profoundly different from the image that ordinary people have, that I had as somebody who'd taken philosophy of science classes and thought I was interested in science, taken some science classes, to the image I had. And I think actually the image, now that I've talked to many different people who have read the book, many scientists, even different from the image that people have as they go into PhD programs in science, become scientists themselves. It takes them a while to kind of see those aspects of science that Kuhn was really getting at in that book. So that was a key moment when I saw it. And of course, there's more to say about what the insight is, obviously, but that was a key moment, to answer your question, when I began to realize that perhaps the most important things about modern science were more connected to the psychological or the sociological, to the institutional framework of science, rather than to the kind of thing that is more traditionally stood out for philosophers of science, stuff to do with the method in a kind of a logical, intellectual sense, a reasoning sense. And so it was a kind of a switch in my thinking from arguing and logic to questions more subtle and background questions about motivation. And that was really when I finally got around to writing the book 20 years later, when I thought it through a bit more for myself. That was above all my motivation. And in fact, one reason why I wrote it as a general audience book is because I wanted to be able to bring in these non-philosophical considerations, the sociology, the history, the psychology, and so on.
Well, I think a big part of your argument is that scientists have to kind of split themselves in some ways, right? Between the way in which they engage the public scientific community, and there's rules around that, and then kind of what they do privately and how they think about things, right? The models that they build in their heads, the passions that they cultivate, the work habits that they have, all of those things. There can be lots of variety there, but when it comes to scientific discourse, there are some very, very rigid rules, and I think that was the piece that was, I think, unrecognized by both Popper and Kuhn.
Yes, that's right. I think that's right. That's my particular contribution. So what Kuhn saw was the importance, not so much of the intellectual side of science, but just motivating scientists to do what's often not intellectually difficult at all, but it's just a really kind of frequently tedious, difficult, susceptible over and over again to failure kind of experimental work they do, a kind of motivational framework. But Kuhn's idea was that ordinary scientists doing normal science are working within this intellectual framework, which on the one hand makes things really easy for them. So this is Kuhn's famous paradigm. They're put into a box, if you like, where the rules are very clear, the goals are very clear. It's almost just like solving a puzzle, and Kuhn makes this comparison, like solving a crossword puzzle even, although a crossword puzzle that takes years and years of work to solve. So, but in a way, it's still hard work, but the foundational issues are all taken care of. But Kuhn thought that box had, if you like, total control over the scientist's mind. So it's not just that their work is in this box, their whole minds are in this box. They can't think outside the box. My idea is that that's not quite right. In fact, there are lots of scientists who are clearly, even just from day to day, thinking outside the box. But they have to kind of, as it were, go back into the box for professional purposes to publish their work. And it's the rules of publication that create this puzzle-like, I mean, that's going a bit too far actually, but this very rigidified, I mean, I do think of it as a kind of a game, if not a puzzle. This game where the rules are relatively clear, but there's only certain kinds of rules, only certain kind of moves that really count, namely making empirical moves. And this is what really gives and the sense in which Kuhn is right is that it gives scientists this security, this huge security in what they're doing, and also closes off all these other avenues of exploration that might seem tempting, so that they just have to throw themselves into their observation, their experimentation, their measurement, and so on.
Well, I mean, other people have tried to define science, right? And they've defined it either through the presence of experiments or the use of math or an emphasis on observation. Why have people failed to recognize this key distinguishing feature of science?
Well, I think because they're expecting it, and hardly surprisingly, to be something intellectual, to be a certain kind of logic or a certain kind of carefully prescribed procedure, to be something that's to something that casts science as one of the great intellectual achievements of the human race. I mean, in some sense, it is one of the great intellectual.
They think of it as a way of thinking, right? Or
yeah, and of course, a lot of thinking goes into science, but a particularly elevated way of thinking. So, and we would mention Popper a little bit earlier. For Popper, it's there's a certain kind of relentless logic to science that's really the most important thing, this desire to prove theories false. And the real mark of a scientist is their application of that logic in a kind of a almost pitiless way to the various theories that come across their lab bench. So people are looking for, as it's often stated, a scientific method, but a method that's more of an intellectual thing. Whereas I think that the truth is, and Kuhn, I think, did see this, the truth is that it's more of a kind of a piece of social engineering, if you like, a piece of social technology, the scientific framework that gives scientists this motivational push that's so crucial in modern science, as opposed to the other kinds of science that preceded it, ancient science in various parts of the world, Greece, China, and so on.
Yeah, I think you quoted somebody who made the distinction between science and scientists, right? And how scientists can be stubborn and bullheaded and have a lot of subjectivity, but that science itself, right, the process ultimately overcomes a lot of those things, right?
Yeah, I think that's right. So, although here, and this is sort of pivoting a little bit from, on the one hand, seeing the short-term problem in science as just motivating the scientists to do their thing, but the long-term effect of that can be a little bit like something intellectual. So scientists are just throwing themselves into their theories. Kuhn thought that for the most part, they weren't even trying to disprove theories or even to test theories. They just took the basic theoretical framework for granted. They weren't trying to test it. They were just trying to use it to solve these smaller problems that were, as it were, set by the framework. So you just assume the theory, you assume that the kinds of structures it gives you to explain things and models or so on are the right tools to use. And then you apply it to these little problems. But the upshot of that is that if there is something wrong with the theoretical framework, because it's being put to use with such determination to succeed, people aren't. If going back to the crossword puzzle metaphor, it's like the scientists really have to finish those puzzles. If they get almost up to the last clue or two and they can't quite make it work, they don't, like an ordinary sensible human being, get up and walk away. They just keep pushing and pushing. And as a result of this pushing, this is why the motivation is so important. As a result of this pushing, they actually turn up these little discrepancies or anomalies, as Kuhn called them, that are ultimately what show that some big theoretical framework, like the framework of Newtonian physics, say, actually has something deeply wrong with it. And that's what brings the old framework crashing down and creates the search for some new framework, like the frameworks of Einsteinian gravity and quantum mechanics that came after Newtonian physics. So at that level, it almost does look like there's this rigorous program of theory testing, but it's not. The scientists themselves aren't necessarily thinking of themselves as testers. They're just thinking of themselves as putting the bits in place in a framework that they take for granted.
So scientific knowledge could advance and progress without any individual scientist ever changing their mind, right? Or being convinced, right? They would just get overwhelmed to some degree, right?
Right. Eventually the framework just, as I say, comes crashing down and there's no framework there to work within anymore. I mean, I think Kuhn exaggerated a little bit the extent to which scientists were kind of fully and totally intellectually committed to the framework. I think there's a huge range of attitudes in science. There's a lot of scientists who it's just their daily job almost, and so they go and do the job and don't spend a lot of time worrying about it otherwise. And then there's some scientists who really feel like they want to make some breakthrough and come up with some revolutionary discovery. All of them have to, as it were, play the same game, and the game works ultimately independently of their personal motivations, simply by generating enough facts with enough systematicity and attention to detail that if there is some problem with the big framework, science will ultimately find it.
And so the idea is that the iron rule requires that all disagreements be converted into empirical ones, right? They all have to be reduced to differential predictions that can ultimately be tested.
Right, and that's the basic rule of the game.
Right. And so, well, I mean, the problem, of course, and I think you highlight this with a number of stories, is that after the experiment has been run, we can kind of backfill reasons why we didn't get the result that we wanted, right? So I always wondered why you didn't see more collaborative research. In other words, you don't usually have people who have incommensurable explanations working together to design experiments so that they can both agree on the method, because then it would make it much more difficult for them to kind of backtrack afterwards, like you saw in the 1919 eclipse story, where if you don't get the results you want, you say, well, it must be a problem with the equipment. Because that's what you see all the time when people don't get the results that they expect to get.
Right, yeah. And so in a way that's because of disagreements that in some sense are kind of reasonable agreements. So sometimes that backtracking can seem kind of weaselly, but I think most of the time it's not. I think in the case of the eclipse experiment, the experimenters, Arthur Eddington and so on, really believed, and in this case actually probably correctly believed, that something had just gone wrong with this set of data, which didn't come out the way they hoped it would, and it couldn't be trusted. So they put it aside. And that happens all the time. Meanwhile, another group of scientists would think, wait a minute, that was a bit quick. But at these stages when science is being made, both sides of a debate like that are somewhat reasonable. Requiring scientists to actually get together and kind of, as it were, agree on how to treat all of these bits of data would, I think, just bring it to a huge screeching halt. So it works much better to let scientists just go off and do their thing, to disagree with one another about how the data is interpreted. It's pretty typical when you talk to scientists in the heat of research. They say, "Oh, so-and-so's lab got this result, but I'm not so sure that was right," and so on. And there's no procedure to settle these disagreements at all. All there is time going on, and crucially, more and more empirical work being done until the facts really start to pile up on one side of the scale rather than the other. And pretty much everyone who's not a crank says, "Okay, well." It looks like, in this case, Einstein was right. We went back and we did more measurements and more again. In fact, it was some of Eddington's critics who actually did the measurements that ultimately convinced a lot of people that Einstein was right about gravity. So, because scientists they are mostly trying to get at the truth. They are responsive ultimately when the evidence piles high enough to these kind of unignorable facts about the intellectual landscape. But it can take a while. There's a lot of disagreement on the way, and nobody ever really goes back at the end and says, okay, so who was right and who was wrong about those experiments? They just move on.
But couldn't we solve some of that with some kind of pre-registration? So we're seeing this movement, right, with pre-registration, where presumably ahead of time you'd have to say, hey, I'm not so sure that these instruments are all that reliable, right? And if you say that beforehand, then after the fact, it sounds a little bit more credible if you say, well, I'm going to reject these, right? But if beforehand you say, I am totally confident that these instruments are great and they're going to work, and then you get the bad result, and then you say, these instruments, problem with the instruments. Could pre-registration solve some of that?
Well, pre-registration is great for some kinds of things, but I don't know that it's so great for these kinds of things. Usually, if something goes wrong, it's something that hadn't been foreseen, or else we would have kind of engineered a solution to it ahead of time. That's not always the case. When they did that 1919 eclipse experiment, one of the things that can go wrong, or that did go wrong, is you get a cloudy skies on the day of the experiment. Obviously, you can't do anything about that. You just have to wait and see. But a lot of these things, with those very data, one of the telescopes, as you were saying, came back with these results that looked like they disproved Einstein and looked like they kind of vindicated Newton. But the photographs were a little bit blurry. What had gone wrong? They went back to the telescope and tested it out again, and it was working fine. They weren't blurry anymore. How do you pre-register a rule for dealing with something like that? It seems like it's just too complicated to kind of write down a decision procedure for absolutely everything that can go wrong. And I think in the end, the actual scientific solution is a better one. It means that a lot of the time in science, it's hard. You get a lot of disagreement about what the data show, but what you do get is science pushes ahead. Because there's no kind of, as it were, you don't have to have an international treaty negotiated every time you want to run an experiment. The data is generated much more quickly, and in the end, it's the amount of data that settles these disputes anyway. So I think that science has hit on a better solution. That's my thinking anyway. It seems to me that's usually true. So we should welcome these kinds of uncertainties, disputes, even the opportunities for kind of, as it were, ass covering and so on. Even if it's not particularly attractive in the moment, I think it actually helps. It helps kind of remove a lot of impediments to the speed of scientific research and actually makes science work better in the long term.
Well, when you publish your results, I mean, should you disclose your motivations? I mean, the iron rule says it shouldn't matter. So the fact that Eddington wanted to kind of create harmony between Germans and the English, and really wanted to bolster Einstein. I mean, when we see a study that is funded by the tobacco industry, for instance, we are likely to dismiss it, right? Because we think that the motivation is a problem. But should we? I mean, should we be required to disclose our motivations? And would it make sense for us to incorporate? One of the things that struck me was the analogy between what you're describing in the world of science and what you see in the world of legislation. So in one school of legislative interpretation, you look at a statute or contract and you're supposed to just ignore, right, what the legislators' motivations are. And then another school says, no, we really need to understand, like, who was it that proposed this, and what were they trying to accomplish? And so those two schools have been going back and forth for a long time. Does the sanitization that you talk about of subjectivity and motivation, is there a potential problem with that?
Well, I think yes. So there is a potential problem, which and you laid it out nicely. On the one hand, knowing people's motivations will really help us to interpret their results more accurately. I mean, not infallibly, obviously, but there's no question. We know from a lot of interesting research that motivations make a difference to how the results come out, even when scientists are acting with a clear conscience, as it were, not just because of dirty tricks. There's just something about it, like referees favoring the home team or something. So that's important information. And it's also true that it's information that's not typically to be found in a scientific journal article, and in fact, in some senses, sort of the genre actively discourages publishing that sort of information. The reason the situation is better than it might sound is that scientists kind of tend to know this sort of thing about one another. So there's a lot that goes into scientists thinking about the evidence, about the evidence that's generated by their friends, rivals, and so on, that's not recorded in the official annals of science, but is still known to scientists themselves, and that they use to interpret these results. I was talking earlier about the scientist who says, well, I'm suspicious about the stuff coming out of that lab. That suspicion can be based on a long history, for example, of trying to replicate the lab's results and failing, and so on. I mean, of course, it might also be completely unreasonable. But this thinking, this much richer thinking, informed by a lot of stuff that's not going into the scientific journals, is, I think, really important to the way that science progresses. In the short term, it doesn't matter that it's not recorded because, as I was just saying a moment ago, it's not a part of science on the whole to kind of resolve what to do about these disagreements about evidence. Everyone just registers their disagreement and keeps on going. And insofar as they agree, what they agree to do is keep doing the kinds of tests that might possibly bear on the question. Then they can get together and argue about those too. Meanwhile, in the long term, when all of these scientists are long gone and nobody remembers anymore what anyone's motivation is, all that's left behind is this record of the evidence. But as I say, it's now the evidence has accumulated to the point, if the science has gone well, when it's kind of more or less clear what the evidence is telling you. So it doesn't matter anymore what this particular lab or that particular run of the experiment produced. The picture is to be consumed on a far larger scale, where this kind of personal information doesn't matter anymore. So again, it turns out that the way that science does things, which looks messy and unregulated and certainly is susceptible to personal bias and so on, actually works out pretty well in the long term.
Mm-hmm. But when scientists are evaluating explanations on their own, right, they will reference things like the beauty or the elegance of a theory or an explanation. And you say that that's you can't ignore that. That is super important. It's just that it can't be expressed in the public discourse. It goes against the rules of the game.
Right. So again, I think that the same kind of observation applies. On the one hand, you can't argue in scientific publication for your theory on the grounds that it's elegant or beautiful in its explanations and so on. But that doesn't mean that when scientists are each doing their own personal assessment of a theory, they won't take that into account. So in some sense, science has it both ways. In the science game insists on empirical testing. So even though Eddington was a mathematical physicist more than anything else, and his appreciation for Einstein's theory was primarily intellectual, he nevertheless found it necessary to organize this whole empirical measurement of the bending of light by the eclipse during the eclipse of the sun and so on that we were discussing earlier. He himself took part in the experiment. He spent 6 months of his life essentially on a boat and on an island in the tropics, setting things up for this measurement because he had to follow the rules. He had to do an empirical test, and that's how we get all this rich empirical data. But then, meanwhile, scientists kind of thinking about what to think about Einstein's theory are totally free to bring in their own minds these more aesthetic considerations that really moved Eddington. So science, on the one hand, forces scientists to do this detailed empirical work, but it also, through these back channels, it gets the benefit of all the non-empirical stuff as well, because that stuff is guiding the scientists in their decisions about what work to do, which theories to take seriously, and so on.
Well, and you describe this as fundamentally irrational, right? And so, I was surprised when I heard that, right? Because that's not what most people think. But the way you explain it actually makes a lot of sense, because you're suppressing all sorts of insights, which normally you don't want to do that, right? Normally you want to actually combine your insights. I mean, you're describing how siloing things actually creates this benefit. And I think most people don't realize this. I don't think I really fully realized this until I read your book, that Newton, who is the paragon of science, the vast majority of the stuff that he wrote, no one ever talks about, right? Because it was sort of outside of this domain for which he's most famous.
Right. Yeah. So he's spent years and years of his life doing experiments in alchemy and so on, and he never published any of that stuff. But then when he goes and does his physics, he's sort of wrote essays disagreeing with Descartes about the nature of space and time. But when he goes and actually does his physics, he doesn't really use any of that stuff. All he cares about is whether his mathematical equations can get the right predictions. And I think in doing that, he really became the person who set up this example of science as a process that was based entirely on empirical reasoning.
Right. So the discontinuity was really not. A lot of people point to Descartes as the person who got the ball rolling, but he was a systematizer, right? He was somebody who was in many ways closer to Aristotle than to Newton in terms of how he would spin out these grand theories of how the world worked.
I think that's right. When it comes to science, it's Newton who's the great discontinuity. If you just have to pick one person, not Descartes.
Even Boyle. I was surprised. Even Boyle was somebody who had sort of a pre-existing view of how the world worked and incorporated that into his publications.
That's right. He did make a big deal about how empirical he was in the way he proceeded, but he didn't. It was more his ideology and his rhetoric. Whereas Newton, we don't find any of that ideology or rhetoric or any such thing at all until much later, when Newton is looking back in his 70s. He just does it. I don't know why, almost out of some kind of instinct. And of course, he's incredibly successful. And so he's kind of showing the way to this new way of doing what he would have called natural philosophy, and we now call science, which has turned out to be so successful. But at the time, it would have been thought, to go back to this irrationality thing, it would have been thought to be a kind of a crazy way to proceed. Clearly, Descartes was doing things the right way. First of all, you kind of figure out the nature of space and time. You figure out what that underlying framework of causal principles should be. For Descartes, it all had to be by kind of pushing, by collision, because he was one of the great mechanists. In that sense, he's quite modern. Then you go to work to sort of start writing down your basic physical principles. And so the philosophy and especially at that time, also to some extent a kind of very intellectualized theology, or certainly just some kind of God who's overseeing the universe comes into the story. All of these things work together to give you your completed picture of the way the world works, just as in Aristotle. And Newton dispenses with almost all of that, even though we can see from his unpublished writings that he took it seriously. For some reason, he just doesn't even bring it into the equation in the first place. And that's, as you say, he's ignoring stuff that he himself thinks is important for getting to the truth about the things he's writing about. Why he did that, I don't know. That's paleo psychology, I suppose. But it turns out to work really well, and that's in effect the way modern science works. It doesn't force scientists in their own minds to be irrational. They can, as we were saying earlier, they can bring in any considerations they like, considerations of aesthetic elegance and so on. But in their published work, it has to be all about just empirical argument. It has to be, in effect, conducted according to the very same rules that Newton set for himself. And it's in that locus of publication, those rules of publication, that's where I am pointing to a kind of narrowness that by excluding things that scientists themselves think are really quite informative, that's where you get a certain kind of irrationality, although a kind of irrationality that actually works to make science more powerful as a way of figuring out the world.
So you can be deeply religious and be a good scientist, just like you could be a good chess player, right? It's independent of the game that you're playing.
Well, I would say it's not totally independent, because in your own mind, that still may have a huge impact. I mean, you might be, if you had a certain kinds of religious affiliations, maybe you just wouldn't be able to even bring yourself to work on evolutionary theory, evolution by natural selection. So it would get in the way of being a good biologist. I mean, the right thing for someone like that to do is find some other area of science to work on, of course. I mean, to some extent, science does encourage scientists to be narrow in their thinking, as well as narrow on the page. But strictly speaking, it doesn't require them to be narrow thinkers, just as it were, narrow writers. You have to. It's actually this is how when you introduced me, the way you sort of started talking about my book. It's like a scientist has these two personas. There's the persona inside their head, where they are a kind of a mathematical aesthete, or maybe a strictly religious in some sense. But then there's a different persona that presents itself when they write up their research. And this persona has no interest in aesthetic arguments, no interest in theological arguments, is 100% totally committed to experimentation, measurement, empirical reasoning. This is their, if you like, every scientist has to have their Newtonian persona when they're writing, to go alongside their real human persona that they have in their thinking.
Now, I think in the 20th century, anthropologists, sociologists, and others have studied scientists, right? And you described how Bruno Latour went to that lab and observed and took notes. And I think out of that research came this notion of radical subjectivism, and the notion that these different approaches to understanding the world, there's no one better or worse way to do it, right? And if you're studying scientists, it's really no different from studying, right, the religious rituals of any group. And I think that Latour described the scientific lab as what it's transforming matter into written documents, right? That's sort of the production process or the ritual that they're engaging in. Um, what is first of all, what are they missing, and why do you think they came to that conclusion? Is it just a failure to understand how science actually works?
Well, no, actually, I think writers like Latour actually are quite insightful in many ways about how the small day to day workings of science go. You know, that's I mean they Latour and other writers like him say a lot of things, but maybe I would zero in on, in particular, on one that's been very influential. That the at the low level decisions about how to think about evidence and theory are as much political as they are logical. I'm not sure Latour ever used those words, but I think that's one of the key observations. And I think the sense in which that's right is that a lot of what goes into a scientist thinking about the evidence is not dictated by some formal logical apparatus or some statistical machinery. I mean, the statistics will churn out some numbers for you, but how you actually regard those numbers, how you treat them, is very much open to you. And what Latour saw is there was a lot of talk about how to interpret these things where issues were coming into the conversation that had nothing to do with logic. Some of them were about the kinds of issues I was mentioning earlier. Is such and such is this process a good way of making this measurement or not, where there's no agreement in the field about exactly how reliable it is or how susceptible it is to error. There's a lot of times when you have to turn some very kind of murky or fuzzy or qualitative data into a kind of something much simpler, like a yes or no. Did we get over the threshold for counting this as a successful test for this molecular structure of some substance? So you're taking something which is a very complicated readout from your machine, and you're saying, is it close enough to this ideal shape that will say, oh yes, we have a positive result, or not? And in drawing those thresholds, there's actually a fair amount of latitude. Actually, this is one of the places where something like pre-registration could make a difference. If you said in advance, here's the line that I'm going to count as going over the threshold. But since people draw different lines, you wouldn't thereby solve the problem of actually agreeing on some particular line that everyone would count as the threshold. So Latour thought there was he called it negotiation about these thresholds. I actually think that's not quite the right word, because mostly scientists as I was saying earlier, there aren't really so many treaties in science that scientists don't. It's not so much that they get together and negotiate some threshold. They just each use their own threshold for various reasons. Some reasons pretty reasonable, maybe some actually quite self-serving. They publish their data using those thresholds. Then they go on and do the next experiment. And these are some of the reasons why you get a fair amount of disagreement on exactly what the evidence is telling you at any particular moment in the white heat of science. So I think that the radical subjectivists, Latour and many other sociologists of science, were right to point to these things as a really important part of the day-to-day reality of doing science.
Mm-hmm. Well, I mean, we've experienced the science wars over the last couple of decades, and I don't think that they're necessarily over. But you wrote, I think, in one of your essays that most scientists don't appreciate the whole field of philosophy of science, right? You know, why is that? I mean, they seem to say that philosophers don't have anything to offer to scientists. I mean, is that true, or I mean, are the philosophers sort of just people on the sidelines, commenting on what's happening on the field, or can they actually serve as coaches to some degree to help scientists do their work better?
I mean, I think science is it has its problems at any point, but it's in reasonably good shape in the sense that there's a sort of an agreed set of rules for playing the game, the iron rule, as I call them.
You you write almost exclusively about the natural sciences. So as a social
That
scientist,
is true.
I would say that it's not quite there yet.
Well, I mean, even something like sort of p-value null hypothesis testing, that has its downside, of course, but it is a rule for doing science, and it's if you just think of it as a kind of a set of boxes you have to check to have research that you can stick into a journal, then I think it mostly actually does what it's supposed to do. With some, it's possible to game it and for things to go south in certain kinds of situations. But as long as you don't take it too seriously as actually telling you something about the intrinsic quality of the data, but just as one sort of basically really just formal threshold the data has to pass. It's like being a legitimate move in chess. Okay, a move can be legitimate and also a really crummy move, and likewise data can satisfy these rules and still be terrible data. As long as you're not too demanding, then these rules apply, I think, across the sciences, at least with maybe the exception of what people sometimes call the humanistic social sciences, like cultural anthropology, which have their own self-understanding and way of doing things.
Well, maybe chess is not the right metaphor, because the rules change over time. When we start to see, in sports, when offense gets too big of an advantage, we change the rules, right? So I think what we're seeing in social sciences and medical sciences, we're seeing the rules changing and saying, hey, that p-value of 0.05 that used to be okay, now we need to have a couple other filters that you have to go through if you want to get published.
Yeah, I think, well, now I'm not going to be talking about how science in general works, but just about my more personal views about how to deal with this sort of thing. I'm inclined to think that the right solution to this problem is not to put additional thresholds on what's going on or to adjust the p-value, but just to have make sure everyone is aware of the context in which these results were obtained. So it continues to be the case that you can publish a result if p is less than 0.05, but we should also know that this was one result that resulted from running our tests on 500 different null hypotheses about possible causal connections between things, or something like that. And so then using that background information, scientists, as opposed to science, can take into account the true significance of passing that test, which may not be very great at all, rather than trying to aim for a rule that's kind of somehow has enough built into it that if something passes the rule, actually that's automatically a sign that this is good data. I think that's basically hopeless. And that scientists are smart enough that they kind of typically know what's going on. I mean, with things like the replicability crisis, lots of people I know in psychology, which is one of the places where it blew up, said, yeah, we've known for ages that many of those results didn't replicate. We didn't, but it's hard to publish a negative result, but in a way it didn't matter because we knew they didn't replicate. At first we thought maybe they did. We got excited, but the first thing you do when you try and build on someone's research is you see if you can replicate it. And if you can't, then often you just move on. And that's typically what's happened. So I think this non-replicable research has done less damage than it looks like looks to people outside of these fields. And the reason is because scientists are smarter at thinking about the significance of data than these publication policies like statistical significance would lead you to expect. There's a lot of savvy and background knowledge that's really going into the way that these results are used, so that they're not having nearly such a deleterious effect on science as you might suppose from the headlines.
Yeah, there's a parable I tell in my class, and I forget who I stole it from, about this, Dr. Dummkopf, who proved that cockroaches hear with their legs, right? You know that story where he went through
No, I
and ripped
don't.
off a leg? So the story goes, he says he has this theory that cockroaches think with their legs, and so he designed an experiment to test it. So he put the roach on the table, banged the table, roach ran away. So he decided to remove one of the legs, bangs the table, runs away less quickly, keeps doing it, and meticulously notes his methods and his procedure, and measures the distance and speed with which it ran and the number of legs and so forth. And by the time you get to 0 legs, he hits the table, the roach doesn't move, therefore it hears with its legs. And so I call that a good scientist, right? Because as long as he meticulously wrote down his methods and included that in his publication, then he's a good scientist, even if his theory is nuts. And we could design a different experiment that would disprove his theory.
Right. That's a great example. And of course, he's going to get a big effect size and a low p-value and all of the good statistical stuff. There's no way that those kinds of thresholds are ever going to show what's wrong with the data. But everyone in your class can immediately see what's wrong with the hypothesis.
Well, you point out that scientists also, most of what they do is really boring. I mean, it's just like Bacon's ants. They just toil away, and it's not necessarily a pleasant job. So why is it that people do this? Partially it's love of truth, but there's also the glory and the fame associated with making your mark through discovery, right?
Totally. There is a kind of a great prize at the end of the whole process.
Yeah. And you highlight in one of your essays that the reward system, which works most of the time, can sometimes give rise to scientific bubbles. And I teach financial markets, and so I was excited to see that you quoted some finance articles about bubbles. Part of that's about the rewards that come from fame, but part of that's also the rewards that come from funding. So presumably the folks who are doing the funding, they're going to fund the things that they think are going to yield the biggest benefit, but they're going to get it wrong sometimes. So how can we calibrate the allocation of research effort to make sure that we're pursuing the frontier which has the highest ROI?
That is a really good question. I tend to think that the scientists taken as a whole are always going to have more knowledge as a whole than some little committee of scientists, no matter how well informed and thoughtful and so on. And so what you want to do as far as possible is outsource these decisions to the scientific community as a whole. But what does that mean? I mean, there's a limited amount of money and plenty of scientists who want it. I have the luxury of being a philosopher in a philosophy department. The way philosophy works is there's almost no funding. But on the other hand, we don't really need a lot of funding. We just need jobs. As long as I can kind of pay the rent and feed myself and have a bit of time to think about stuff, then I can come up with my ideas. And if I come up with good ideas, then that's great. We will, if we philosophers see a good idea, we'll start thinking about it. A fruitful idea, if we're right, we'll get something out of it. That all works because it doesn't really, it's not true there are no startup costs, but they're not that great. It's a little bit like the kind of old days of tabletop science when you would just sort of think, oh, that'd be interesting to work on that, and you get a few bits of wire and a beaker or two and I don't know what, and tie it all together and start doing your experiments a week later. But in a world where doing science costs millions and millions of dollars, it's not so easy to just leave it up to the judgment of scientists as a whole. It's a tough problem, but on the whole, I think it's good not to sort of try to pick out just a few projects and funnel everything towards those few projects. I'm afraid I don't have too many good ideas about the alternative apart from that, except to allow diversity to flourish in one way or another.
Well, you also talk about armchair philosophy and defend it. What's the alternative? I mean, I know there's this movement in experimental philosophy, but I think you're making a bigger point about armchair philosophy, about the idea that conceptualizing, seeking explanations, and trying to grasp concepts. This is something which which is super valuable. Um, what is the alternative to armchair philosophy, and why does it need to be defended?
Well, I'm certainly not against non-armchair philosophy. Actually, part of the twist in my defense of armchair philosophy is that it's based in empirical psychology. So the book Defending Armchair Philosophy is not itself armchair philosophy. And that's nothing wrong with that. But I was just
How
interested
empirical
in whether
psychology vindicates armchair philosophy.
that's my subtitle. Yeah, how empirical psychology vindicates armchair philosophy. So I was interested as somebody who's obviously interested in science, but doing philosophy, how it could ever be possible to do something really new in just by thinking. I guess we have some examples of that. Mathematicians do come up with new theorems just by thinking. Philosophers have certainly come up with interesting problems just by thinking, but could we actually could we happen upon new knowledge just by thinking? And you might, if you look at what philosophers actually often do in their armchairs or their desk
I mean,
chairs, more
you're
typically.
describing Descartes, right? I mean, Descartes was
Yeah,
the ultimate armchair philosopher. I mean,
right.
he did dissect brains and
Living,
did some other stuff, but I mean, for the most part, he was spinning a web in his chair.
and this is back in the 1600s when a whole range of philosophers still really had this faith that just by thinking through things you could get the structure of space and time right and see through to what causation was all about, just to go back to those earlier topics. And in a way, Newton came along and said, no, actually, you don't have to do any of that. In fact, it works better not to do that. And that's when, that it's around then that I suppose philosophy went into permanent crisis. Uh, at least as far as thinking about its own ability to actually determine how the world works. And what you have after that, after Newton, is a couple of hundred years of the most philosophers being one way or another giving you some version of the story that actually you can't just by thinking figure out anything about the world.
Well, you wrote an essay on grasp and understanding explanations. But I mean, how does an explanation differ from a prediction? Because it seems that you can be a powerful predictor without actually having an explanation, right? So if you think about machine learning algorithms, they
Yeah.
can do a fantastic job. I think you described in one of your essays about sort of a scanner, someone who just looks and can identify this is a dog, this is not dog, this is a cat, this is not cat, right? And
Hmm.
they don't have any explanation. If you ask the machine to explain what it's doing, it probably can't. I mean, ideally it could, but it doesn't always have the capacity. So, I mean, first of all, how do we even know if someone has an explanation and has a grasp of a concept if we're just observing their behavior?
Well, that is pretty difficult, of course. But the machine learning example is a good one. So take one of these new machine learning models of, say, that does weather forecasting. Say, it seems that they actually work just about as accurately and using much less energy to make weather forecasts as just basically by learning from a huge data set and picking out really complicated correlations. As they're much more efficient, it seems, than traditional weather forecasting models that actually try to figure out, based on the physics of atmospheric flow and so on, what's going to happen. Um, so you have those two kinds of models are both very good at prediction. But if you actually want to understand why the weather is the way it is, you need to go to the inefficient model, the one that really kind of has the physics in it that says, oh, well, you see what happens is when you have these kinds of convection in the atmosphere, blah, 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 however it goes. That's explanation, that's understanding. That's something that isn't necessarily going to make your predictions for the picnic and the weekend any more accurate, but it gives you this intellectual fulfillment that we also hope to get from science, from all of the intellectual pursuits. This sense, oh, I see how it works. So that work of mine on explanation and understanding and grasp and so on is supposed to say more about what it is, what this positive thing we're getting out of the old causal models is, that just isn't even, it's not anywhere to be found in the machine learning models.
And so I want to ask you just a bit about teaching,
Mhm.
because this idea of the scientific approach, I mean, this is something which can extend beyond what we normally think of as science. I teach in business classes, and
Mhm.
I teach the case method. And you talk a bit about Charles Peirce and sort of reasoning through cases. And um, when I have my students debate with each other, um, it takes a long time for them to realize that most of their disagreements are empirical ones. They think that
Mhm.
they're disagreeing on all sorts of other things. And it requires quite a bit of effort to get them in the habit of reducing their disagreements to things that can
Mhm.
be tested empirically. Why is it, it seems unnatural? I think that's part of what you're arguing in the book. And so do we just have to continuously be vigilant when it comes to fostering these productive dialogues in all
Hmm.
areas, not just in what we might think of as mainstream science?
That's interesting. Yeah. So, one way to read my science book, or just to read the history of science, is that what were until the 17th century seen as philosophical clashes to be resolved by thinking about what principles were the right principles for understanding how the world worked through philosophical debate. In effect, we had to science. What people like Newton figured out was how to turn those into experimental tests. We could just sit down and kind of, as it were, do the experiment. Well, as we were saying earlier, it's not quite that simple because experiments go wrong, but eventually pile up the data there's that will resolve the question. So is there something about you're asking me? Is there something about regular
Well, because
people
in order
that
to
makes them
convert it
more
into it,
inclined to think philosophically than empirically about these questions?
well, it seems that in order to convert something into something that can be empirically tested, you have to spend some time elaborating the the predictions, which means you have to actually
Right.
work through some theory which says this is what I expect to see. And so there has to be ultimately some agreement by the different people as to what would constitute a legitimate test. And it seems like that requires an awful lot of work that that a lot of people aren't interested in doing. And is it because it's counterintuitive? It's something that is difficult for us as humans to engage in. Why is it not something that is more natural?
Well, I wonder. I mean, one possible explanation is that doing the empirical work itself is not very rewarding. It's much more fun to have a philosophical argument than to sit down and do what you do in a physics lab. So it's not so much kind of figuring. It's not so much that you can't figure out how to turn your question into an empirical experiment, is that you kind of don't want to have to end up just sitting at the lab bench, kind of trying to make your numbers come out right when you could be waving your arms around and thinking big thoughts. I mean, I think to some extent this is the answer to the question why modern science, took so long to come along, because it's just so much more fun to philosophize than
Yeah.
to sit in the lab day after day getting your apparatus to work properly.
Well, if it's only been in the world of science for the last 300 years, it's only probably been in the world of business for the last, couple of decades. But that is
Yeah,
now sort of
yeah.
how successful business is run. And certainly in the
Hmm.
startup world,
Hmm.
what
Hmm.
every founder is running is effectively a lab where they're
Hmm.
testing hypotheses. And so if
Hmm.
there's a disagreement about whether or not they should go B2C or B2B, or if they should target this audience, that audience, those things are generally resolved with empirical tests now. And it's the venture capitalists that are pushing them to use
Uh-huh.
the empirical tests because they're not willing to fund um, the pursuit of something which doesn't have any empirical grounding. They're going to run out of money real quick if they do that.
So do you think it's right then that I'm thinking of all those business books from last century. They're all about are kind of like big, fun, exciting ideas. That stuff just seemed so much more attractive than sitting down and compiling the statistics on this technique versus this technique. And it's taken a long time for people to realize that they have to do the boring stuff if they're going to get the answers to the questions that they're asking.
I think that we just hadn't yet developed the technology that enabled us to do this cheaply and at scale. And so now that's much easier to do. It's like having a lab at your fingertips, right? And methods that are at your fingertips. And so now if you don't do that, then it's highly unlikely that anyone's going to fund you. So every founder and entrepreneur now has to be a scientist as well, and has to incorporate this way of thinking, even though they're not publishing anything. They still have to follow these rules if they want to publish it. I guess they publish it in the form of their next pitch deck, right? Which is what they show to the VCs. And if it doesn't pass muster in terms of adhering to the scientific method, then they'll be unable to convince anybody to give them their next round of money. So
that's really interesting.
Well, Michael, thank you so much. This is fantastic. This is one of my favorite books of the year. I really appreciate you writing it. Thanks so much for joining me.
Oh, thank you. Thank you. This has been a lot of fun.
Unsiloed podcast is produced by University FM, elevating the stories of your institution.